An atom is defined by its number of protons. An atom is defined by the number of protons. This implies then two different atoms have different amounts of protons. On the other hand, two elements can contain the same number of neutrons because isotopes have different number of neutrons. Isotopes can have the same number of neutrons. Example: hydrogen (3) looks something like this. So it's 3H1 versus helium 4, which is 4,2H2. So if I calculate the number of neutrons and protons, I have 2 neutrons, 1 proton, and in this case I have 2 neutrons, 2 protons. So you're seeing here is that they have the same neutron number, but they have different proton numbers. Question 2. The nuclear bomb that was dropped over Nagasaki, Japan in 1945 used a plutonium-239 bomb. Determine the number of protons, neutrons, electrons, orbitals, and if this form of plutonium is the most common. First of all, I got to find plutonium-239. So typically what you want to do here is that you want to go to the periodic table and look for the atoms that have masses of the order of 239. And when you go all the way down to the 7th row, you'll see here that plutonium turns out to be atom 94. So now, putting this atom in atomic spectra notation, here I go. So I write 244, 94, plutonium. So this one is from the periodic table. And so when I look at the periodic table, if I calculate the details on this one here, I'm going to get 0, and then I'm going to have 90 neutrons. Oops. Made a math error there. So if I'm going to borrow 1, then I'm going to get 150 neutrons, 94 protons, equal to the number of electrons. Now if I go and I look at its orbitals, plutonium is on row 7. So this guy, it's on this row right here. So there's plutonium, and this row here is row 7. So now I'm going to look at the one listed in the question. The question says that this form of plutonium, so the plutonium in question is 239.94 Pu. Note, 94 tells me it's plutonium. So now if I calculate the details here, I'm seeing here that I have 5, then I'm going to borrow 1, and then that's going to be 1 neutrons. I have 94 protons, 94 electrons, and again, it's 7 rows. It's on the 7th row, so therefore this tells me there are 7 shells. So when I look at this thing here, the two things that I need to compare is that neutron number to that neutron number. Because (239) plutonium is different than 244 plutonium, it's the number of neutrons. That determines the isotopes. So these are two different isotopes. But there's a problem here. The problem is that because plutonium is so far towards the bottom of the table, it is impossible to tell whether this is the most common isotope or not. So the answer to this thing is that we don't know the most common isotope because it's far towards the bottom of the table. Furthermore, this atom is radioactive and does not exist naturally in nature. Problem 3. To date the age of the Earth, geologists use a radiometric technique. One technique is the lead-lead radioactive chain, which essentially compares lead ratios of 204, 206, 207, and 208. Which of these is most common isotope of lead, and lists the number of protons, neutrons, and atomic orbitals. So, looking at the atomic masses of 204, when we go to the periodic table, we have to go look around those masses here. So if you go in, you'll see that lead is somewhere is on the 6th row here. And so if I look at what I see on the table, here's an image of what that looks like. So if I look at the table, this tells me that I'm going to get this guy right here. So writing up in spectral notation here, I find that this guy has 207, 82, the element lead. So now if I subtract that, I'm going to get 5. I'm going to borrow 1, which then gives me 1 here. So therefore, I'm going to get 125 neutrons. But because this is lead, I know that this has 82 protons, 82 electrons. And then if I look at lead over here, you could see here it's 1, 2, 3, 4, 5, 6. It's on the 6th row, so therefore it has 6 shells. So this is the one that's on the periodic table, and the first thing that I would warn against, because this is the 6th shell, that means most common is not likely to be this isotope. But we'll look right now. So now what I want to do here is that I want to look at the 3 other isotopes. So I have 204 lead, 206 lead, and I have 208 lead. So when I look at this thing here, they all must have the same protons. So I know that these guys here are going to be the same. So they're the same for all isotopes. So the only thing that's going to differ here is the number of neutrons. So let's calculate the neutrons in each of these cases here. So I know that each of these has 82 neutrons. So let's go calculate the number of neutrons here. So then this guy's going to give me 122 neutrons. This is going to give me 124 neutrons. And this one's going to give me 126 neutrons. So when I compare the number of neutrons, so if I look at this guy here, and I compare them to here, here, and here, we see that each isotope of lead has different number of neutrons. So in lecture we talked about that typically the most common one is the one that's closest to the one on the periodic table. Okay, but one of the hints here comes in the atomic mass number that you see on the table. So the table isotope is the average of all isotopes. And that number, if you look at it, says 82 PB, and then the number that you're seeing here reads 207.20. The fact that this number is larger implies there are isotopes heavier. And from Wikipedia, okay, so I got this off of Wikipedia right here, and you could see that the most common in nature is 208 lead. Problem 4. The atoms that compose your body are mostly empty space, and structures such as